Starting with the IB Mathematics Standard Level course, now we are going to talk about exponential functions, which is in class 4. We have a good base now in functions and linear equations, quadratic equations. Now we need to know more and to know very well exponential functions. We can start with the general form of the exponential function is like we have f of x is equal to a times b to the power of x plus c. This is our general form. If we go directly to the behavior of any function, let's say we want to see the behavior of fx is equal to 2 to the power of x. If we want to sketch this function, we can sketch it this way. So draw, this is one, and let's draw the other axis. Our sketch would be like this, where I'm having a horizontal asymptote at y equals 0. We'll see why we are having a horizontal asymptote at y equals 0. If we want to inspect this function, we must test for the infinities. This is the y-axis and this is the x-axis. We must test for the infinities. Let's check as x goes to positive infinity, what happens to the function? I want to find f of positive infinity, which is equal to 2 to the power of positive infinity, giving me a positive infinity. So when x is equal to positive infinity, the value of y here is positive infinity. So I have a positive infinity with a positive infinity, which is a point somewhere here. Is a positive infinity with a positive infinity. This is my point. This is a positive infinity with a positive infinity. If we want to check, I'm having here an intersection at the y-axis. The intersection at the y-axis, it means that I'm having an x value of a 0. So let's check f of the 0. F of the 0 is equal to 2 to the power of 0, which is equal to 1. So this point is a 0 with 1. Now let's check as x goes to negative infinity. I'm having f of negative infinity, which is equal to 2 to the power of negative infinity equal to 1 over 2 to the power of positive infinity, which is equal to 1 over a positive infinity, which is approximately equal to 0. So since it's approaching 0, as x goes to negative infinity, the function approaches 0, I'm having here a horizontal asymptote at y equals to 0, which is this. This is my horizontal asymptote. This is my exponential function. This is my exponential function. If we want to find the inverse of the exponential function, we will talk about logs. We will talk about logs. So we can draw again. This is my function. Yeah. And this is the exponential function, and if we want to draw the inverse function, which is a reflection on the line y equals x, we'll have the log, which is this way. The red function, so that is 2 to the power of x, and the green one is log x to the base of 2. Here I'm having an intersection at 0 and 1, and this value is 1 with 0. If we can see, for the log function I can't have a value, negative value in the x, and it can't take a 0 because here I'm having an asymptote for the log at x is equal to 0. What's meant by log? When I say log, let's say I'm having log to the base 2, log 8 to the base of 2. What does it mean? It means 2 to the power of what value gives me an 8. So I will have a value here of 3, because 2 to the power of 3 is equal to 8. For logs, if I don't have a base, let's say I'm having log the 100, I don't write the base. The default base, if not writing a base, is 10. So a log of 200 means 10 to the power of what gives me 200, which is 2. This means 10 to the power of 2 is equal to 100. Let's check some rules of logs. If I have log A plus log B, when I have a plus sign between two logs, it's simply equal to the log A times B. This is rule number 1. Rule number 2. If I have log A minus log B, then this is equal to, when I subtract, I divide the values inside, is equal to log A over B. Rule number 3. If I have log A to the power of B, this is equal to B log A. I can take the B down here, I multiply it by the log of A. The last rule, which is change of base rule, if I'm having log A to the base B, this is equal to log A to the base X over log of B to the base of X. These are my rules for logs. Let's continue. If I'm having a log with base E, let's say log 2 to the base E, this is the same as I'm saying it's len 2, which means that the len is the same as a log with base E. it's essential to use len. If we want to draw the function len, let's have the axes. I'm drawing. These are my axes. And draw. Say this function, the red one, is e to the power of x. And I want to draw the len function because it's the inverse of e to the power of x. This is len of x. This value is a 1 and 0, and this one is a 0 and 1. For e to the power of x, I'm having a horizontal asymptote. At y equals 0. And for the len of x, I'm having a vertical asymptote at x equals 0. The rules of dealing with len are the same as the rules of logs. And even the sketch of function is the same. We can see here, this is 2 to the power of x and log base 2 of x is the same as this function of the len. By this, we've covered the rules of logs and len. There are 4 rules and the sketch of an exponential function and len. For transformations of this function, we'll come to it later. Now let's solve a question. This question is also from the question bank. We can start with, we have the number of bacteria in 2 colonies, A and B, starts increasing at the same time. The number of bacteria in colony A after t hours is modeled by the function. This is the number of bacteria. A as a function of t, which is hours, is equal to 12 times e to the power of 0.4 t. Section A. Find the number of bacteria in colony A after 4 hours. Simply I substitute in my formula. I want to find A of 4. A of 4 is equal to 12 times e to the power of 0.4 times 4, which is equal to, we need our GDC here. This is on. It's 12. Second, e to the power of 0.4 times 4. Equal to 59.4. We can approximate it. The answer is 59.4, which is equal to 59. This is part A. Can go to part B. Find the number of bacteria in colony after colony A after 4 hours. Yeah, as the part B is the same as part A. There is something wrong in this question. So is A of 4, which is equal to 12 E 0.4 times 4, which is equal 59.4, approximately is 59. Part C now. How long does it take for the number of bacteria in colony A to reach 400? This is a very, very good question. To reach 400, it means I want the whole function to be equal to 400. So I want A as a function of t to be equal to 400. Good question. So we'll say that 400 is equal to 12 e to the power of 0.4t, divide over 12 over 12. This will cross out. 400 over 12 is equal to 33. We can keep it like this. We can keep it as a 400 over 12. So I'm having e to the power of 0.4t is equal to 400 over 12. To get rid of the e, I need to use len for both sides. So I use len here and len here. This len will cross out the e, so I'll have (0.4t) equal to len 400 over 12. To find t, simply I have to divide len 400 over 12 over 0.4. So t is equal to len the 400 over 12, all of it divided by 0.4, which is equal to, we have to use our calculator. I need to, this is the len 400 over 12 is equal to, and the answer I must divide it by 0.4. It's 8.77. So the time needed for colony A to reach 400 is 8.77. 8.77 hours. This value is rounded to 3 significant figures because we always need to round to 3 significant figures. Let's do part D. Part D, the number of bacteria in colony B is modeled by the function, this is B as a function of t, equal 24 e to the power of kt. After 4 hours there are 60 bacteria, find the value of k. Okay, then after 4 hours we have a 60 bacteria, which means I'm having the B of 4 is equal to 60. B of 4 is equal to 60 means that when I substitute a 4 in my function, the value of the function is 60. My function is, I have 24 e to k times 4 is equal to 60. Now we have to divide over 24 over 24. These will cross out. Now I'm having e to the power of k times 4 is equal to 60 over 24. To get rid of the e, I need to use len for both sides. This len with the e will cross out. To continue, now I'm having 4k is equal to len 60 over 24. To find k, I divide by 4, so k is equal to len 60 over 24, all of this value over f4, which is equal to, we use our GDC, we need to find len 60 over 24 is equal to this value, and I have to divide this value by 4. It's equal to 0.229 to 3 significant figures. 0.229, this value is also to 3 significant figures. Part E, the number of bacteria in colony B after T hours is modeled by, same model. We found the value of k is 0.229. And you have the number of bacteria in colony A first exceeds the number of bacteria in colony B after n hours, where n belongs to z. Find the value of n. We need to find when the value of bacteria in colony A, the time of when the value of bacteria in colony A exceeds the value of bacteria in colony B. If we're having the function of colony A, number of bacteria, so for part E, we need to find that when the number of colony A, which is e to the power of 0.4 t, exceeds, which is greater than, when I say exceeds, it's greater than the value of bacteria in colony B. The function in colony B is 24 e to the power of 0.229 t. I want to find the value of t such that function A is greater than function B. To continue with, first divide both sides over 24. This is over 24 and this is over 24. We'll have half e 0.4t is must be greater than e 0.29t. I want to find with this function the time when this function is greater than this function. In this way, now either we take len, or we can sketch both of these functions on my GDC and I can find the answer directly. Let's try our GDC. For the GDC, we go to graph, the second, and graph. I have to clear this. This is a table without the second graph. We go to graph directly. See, here I don't have a graph. So in order to plug in a value for the function, I need to go to this button, which is y equal. I have my y equal, this is y1. I put this 0.5 times e to the power of 0.4. t is my variable. I can use here the x. for the variable. I use this x. This is my first function. For the second function, I press an enter. I go to y2. y2 is e to the power of 0.229 t. So second, e to the power of 0.229 and plug the x. It's our variable. These are my two functions. To graph them, I go directly to graph. Now I'm having these two functions. But if you can see here, the intersection would be in the positive value because I need the t to be positive value. So I need to fix the window. Let's say the x minimum, I plug it as a 0. This is enter. I go down to the y minimum and I make it as 0 as well. Graph. I'm having a better view now. The first function is function number 1 and the second one is the B colony. I need to find this intersection because after this intersection the number of bacteria in colony A will exceed the number of bacteria in colony B. I go to second, calc, and to number 5, which is intersect. I press 5. The calculator asks for the first curve, which is yes, this one, enter, and the second one is down, and the guess I want to go to the intersection place, and I press enter again. So what's the time of intersection? I look at the x value. It's 4.05. So when time is 4.05 hours, colony A will exceed colony B number. So T, the intersection, I'm having T equal 4.05 hours. Let's check our question if it wants an integer as a value. After n hours, where n, a number of bacteria exceeds the number after. If it asks for n hours, integer values, we can say that we are having an intersection at 4.05, so after time of 4.05 hours, the colony A exceeds, which I can take it like at t equal 5 hours, the number of colony A bacteria exceeds number of colony B bacteria. I hope it was useful. This is a very good question, and the skills used in our graphical display calculator is essential to solve such type of questions.